Thank you very much. Birds of a feather flock together, or so the saying goes. And as we hear this idiom, you might assume that its origin is because birds are highly sociable creatures, which of course they are. But over the last century or so, both engineers and biologists have clearly demonstrated the enhanced propulsive efficiency enjoyed by birds flying in formation, schools of fish swimming together, or flies or swimmers operating close to a ground plane. And these so-called propulsion strategies are currently enjoying renewed interest as energy-saving techniques become more and more crucial. But unfortunately, analytical techniques that usually elucidate the underlying physics of these kind of problems and are very successful for single-body configurations suddenly break down when we introduce a second, third, or fourth body due to the change in topology of the problem. But today my aim is to introduce you to a couple of basic aerodynamic techniques that show that simply connected, that is a single body, techniques can be extended to multiply connected, that is multiple body problems. And we're going to be focused on ground effect for an example. And that's basically because it's the simplest non-simply connected domain. And the two phenomena we're going to study are vortex equilibria and small unsteady motions. So firstly, the vortex equilibria. There's been quite a lot of work done in the last 15 years or so on multiply connected conformal mappings, and this has predominantly been undertaken by Darren Crowdy at Imperial. Just a few publications here. I could have put 15 to 20 more on there. And he's really discovered a lot of properties of this transcendental special function known as the Schottky-Klein prime function. And it turns out that this function is, in fact, a fundamental object in complex variable theory and can be used to study many multiply connected problems. So the typical approach is to begin with a canonical circular domain, that is the unit disk with several x-sized circles, and then to construct a conformal map from this canonical domain to the domain of interest. So here are just a few examples you might be interested in. So we've got aerodynamics, insect flight, turbomachinery, formation flight, what we're thinking about today. But as mentioned, we are interested in the ground effect problem. So something we've done is to derive or discover a new conformal map that maps this canonical circular annular domain to a flat plate above the ground, modeling something flying close to the ground plane. And this is really, the map is simply given by this. So it's just the ratio of two prime functions. And the second parameter in the prime function is used to set the angle of inclination that the plate is at. And then this q, the radius of the interior circle, is used to define the distance away from the ground. And now we have this conformal mapping, we can set about studying the vortex equilibria. So we say that a point vortex is in equilibrium if its desingularized velocity is 0, i.e. if it is stationary. And we also specify that the vortices must satisfy a cut condition, so the flow at the sharp trailing edge must be smooth. And these vortices can be very useful practically because they can enhance the lift exerted by an aerofoil for a given speed. And they've been found experimentally as well. But the first analytical treatment of these was undertaken by Safman and Sheffield, where they used the Joukowsky map to find the equilibrium configurations for a plate just in free space. And the map that we found is really an extension of this Joukowsky map. So you can imagine all the research that's been done using the Joukowsky map. There's some stuff outside, for example, can now be considered for a flat plate in a ground, next to a ground plane as well. So it's potentially a very useful map. And anyway, what Safman and Sheffield discovered was that there were two loci of vortex equilibrium positions, one connected to the leading edge of the plate and one connected to the trailing edge. And these are some of the streamlines of an equilibria at the trailing edge. So in order to calculate the complex potential, we again use the prime function. And Crowdy has developed this new calculus of vortex dynamics that allows you to construct the complex potential for these kind of problems. And that allows us to get flows such as this. So we've always got uniform flow from left to right in this potential flow. And on this one, on the left-hand side, we've tuned the circulation around the plate so that the cut condition is satisfied, so you can see the flow leaving the trailing edge smoothly. And then on the right-hand side, we've introduced some point vortices into the flow. But if these vortices are to be in equilibrium, then they need to satisfy three equations. Firstly, the velocity in both the horizontal and vertical directions needs to be 0. And secondly, they have an equation for the cut condition. But we have four unknowns. We have the two coordinates of the vortex, we have the intensity of that vortex, and the circulation around the plate. And consequently, we expect there to be loci of solutions again. But actually finding these equilibrium configurations is not straightforward because we have to solve a rather complicated equation. But we overcome this by using the method of Brownian ratchets. And this is a method that involves sending possible equilibrium configurations on a random walk and calculating the variance of that random walk by using something called the singular values of the configuration matrix. So the role of this diagram is twofold. Firstly, it shows the image of radial lines under the conformal map. So you see these lines intersect at right angles with both of these black lines. The interior one corresponds to the plate, exterior to the ground. And we have similar behavior in this plane. But when I click on it, it's going to show the convergence of the algorithm. So you can see these particles all going on random walks, and very quickly they converge to what appear to be three loci of solutions. And if we were to let the algorithm continue until the singular value was something close to machine precision, then we would see that there are, in fact, three loci of solutions. So in contrast to the classical case of Safman and Sheffield, where they just had the leading edge and the trailing edge vortices, there are now these blue ones as well, which are unattached to the plate. And these could be very useful in controlling the lift for objects flying close to the ground. A couple of probably unrealistic practical consequences, potentially reduce takeoff and runway and landing distances because we can enhance the lift on these plates or planes for a given velocity. So that means that you can shorten the runway and potentially the control of lift on race cars as well through the shedding and feeding of vortices. And here are a couple of pictures of what the streamlines look like. So you can see it's very smooth at the trailing edge. And these are the trajectories of the vortices. So on the left-hand side, it's a saddle point. So if you perturb it, it's going to go off on this orange trajectory. And this guy on the right-hand side is neutrally stable. Now, onto small amplitude oscillations, which is the second model that I mentioned. So now we can forget about all the conformal mappings and the trapped vortices. Now we have an airfoil inclined above the ground, which is heaving, so its distance above the ground is changing, and it's also pitching, so its angle is changing as well. And this can be extended to any number of airfoils in any positions. And again, the flow is potential, and we have this kinematic boundary condition on each airfoil surface. And the vortex shedding is now modeled as an unsteady wake emanating from the trailing edge of the airfoil. And as far as previous work is concerned, there's been quite a lot done into the extreme ground effect problem, that is d much less than 1, and a bit of work done into the weak ground effect problem, that's d greater than 1. But as you can see, there's quite a large gap here where for d between 0 and 1, not much has been considered because the equation is very difficult to solve there. And consequently, the present analysis will be valid for all scales of d, so all along this diagram. So the solution method is to extend the classical thin airfoil theory to include multiply connected domains or multiple oscillating foils. And the way this typically works is to construct a singular integral equation, or equivalently construct the Riemann-Hilbert problem for the bound vortex distribution, that is gamma, on the chord of each airfoil to obtain a singular integral equation. And then we can solve these using weighted Chebyshev polynomials. But when we have multiple airfoils, this system becomes quite difficult, and you have a lot of double integrals. So we've derived a new identity for Chebyshev polynomials, which allows us to reduce the number of integrals needed, resulting in an infinite-dimensional linear algebraic system for the AN, which we can truncate and then solve easily in MATLAB. And the last bit to do is to apply the Cutter condition and set the intensity of the wake, which we do using Kelvin's circulation theorem. So draw a big loop around the airfoil and the wake and say the circulation is 0. And this gives us a modified version of the Theodorson function, which relates the quasi-steady lift to the wake-induced lift. And quickly, here are some results on the lift as a function of distance above the ground, so pitching on the left-hand side and heaving on the right-hand side for a variety of Strehl numbers or reduced frequency. So to conclude, we've shown how a couple of really basic aerodynamic techniques can be extended to take into account multiply connected domains. We've used ground effect as an example. We studied the vortex equilibrium configurations for a flat plate in ground effect and discovered a new set of equilibria, which could have practical consequences. And we found the fresh field and the vortex distribution more precisely for an airfoil undergoing small amplitude oscillations in ground effect. And finally, the next thing I'd like to do is to combine these two approaches and model the wake shedding as Brown-Michael vortices using this conformal map depending on time. So thank you for listening, and are there any questions?
I'll jump in with those last results you showed. Very impressive with the variation of CL. What validation do you have for those?
This is just totally theoretical. I don't know if there are some experiments in numerical things for just the pitching motions that I'd like to compare to, but no validation yet. Yeah, I don't know if there are any other analytical models that would take this into account.
Very difficult to recreate something two-dimensional, potentially.
Yeah. And you can use the vortex distribution to calculate the thrust and the power and the propulsive efficiency, things like that.
When you have this heavy motion, do you have this trapped vortex sitting?
No, they'd be disturbed. Yeah, they wouldn't be there.
Hi, my name is Weidong Dai, and my topic is stability in the boundary layer and wake of oscillating foil at moderate Reynolds number. It is a collaboration between myself, my supervisor Dr. Viola, University of Edinburgh, and Professor Ballaras from George Washington University. Oops, sorry. You might be familiar with the concept of wind turbine, but what we investigated is similar concept, but under the water. So we have tidal turbine, and the main constraint we have compared with wind turbine is that we have free surface. So particularly what the free surface do is to induce flow velocity variation. So on top of this, the turbine is working in the boundary layer of tidal channel, which means you have low velocity near the seabed and high velocity near the free surface. And when the blade rotates, it will go across from the region where there is high velocity to the region where they have low velocity. And the third source of load fluctuation is due to the turbulence. So all those three altogether lead to the variation of angle of attack. And this variation lead to the variation of loading, eventually to the fatigue failure. So in order to prevent fatigue failure, what we want to do is to develop a technology which is called passive pitch. So basically, you will have a blade able to pitch around its spin-wide direction. And when the flow changes directions, the blade pitch to accommodate the variation of angle of attack, so keep the angle of attack constant. So you will get this angle of attack variations over period resolution. And when you have the pitch control, it can completely cancel the variation of angle of attack. But the problem is when we try to explore this new technology, we need to do some experiment in small scale facilities. And when we take this large tidal turbine over there into our small scale facilities, the Reynolds number goes down very quickly, basically from 7 million to only 10,000. So which means you come from a Reynolds number regime where it's very well understood, where the boundary layer are fully turbulent and most likely attached, to Reynolds number region where you have laminar boundary layer and you can have separation. And when you have separation, you can have transitions. So what we want to do now is to investigate it. If we have the correct tools to investigate this pitch control mechanism, and what is exactly the physics at this moderate Reynolds number. So the first things we do is to consider a small angle of attack variation. So we set ourselves in on the reference system of the flow. Then we have uniform flow and oscillation foil shedding vortices, but in this case is in weak. So then we measure the drag force. So you can say the faster you pitch the foil, the lower drag force you can get, and eventually it becomes negative, which means you switch from a condition where you have drag resistance to a condition where you have propulsion. So when you check those plot here, those light or green plots are experiment data from literature. You can see there is very significant scatter in those experiment data, which demonstrates the difficulty to performing experiments. However, when you check numerical result, which are those blue plot here from literature, and my result are those orange plots. So it seems like the numerical method works very well in predicting a constant curve over frequencies. So take message from here is as long as the angle of attack is small, even very small changes in the force on the body can be very well predicted numerically, even more accurately than to be done experimentally. However, when we have large angle of attack variation, in this case we have a flat plate, its pitch around its leading edge to 25 degrees, keep it constant for a while and pitch back. So in this case, angle of attack is large enough to have separation. When we check the results, when we check the result from the literature, you can have the one experiment data and one numerical data. Here you can see the differences is large, especially here it's almost, for the lift coefficient here is almost 0.7. So here he used Ray's simulation, and we know Ray's has been developed for very high Reynolds number, where the flow treated as fully turbulence. So what we want to do is to explore a more sophisticated numerical method to explore this physics. So the first things we want to do is we still use Ray's, but we add a transition model, and the second thing we do is large eddy simulation, and the third thing we do is, of course, direct numerical simulation. So here is the result from the Ray's simulation with transition model. You can see here they pretty much the same as one without transition model. It seems like there is no significant gains has been achieved with transition model. Then we check the direct numerical simulation. Because here I only show DNS result, as LES more or less give you very similar result. So when you have a DNS, there the transition is captured without model. It is resolved by numerical method. So the transition can only be seen when there is breakdown, and you can see the instability in the shear layer and the breakdown of the vortex structure here. But however, when we check the result here, so we can see the force here is, there is no significant change here, only here. We definitely get close to the experimental data. So we come to the conclusion that at moderate Reynolds number, at very low angle of attack, the flow remains laminar, and we found very good experiment and numerical agreement. However, when the angle of attack is large, the separate shear layer become unstable, become turbulence. So the disagreements between numerical and experiment data are significant, and we managed to half of the differences, but still not enough, which made us believe what we need to do the next step is to look into a new set of experiments where we can control accurately the uncertainty of experiment. Thank you.
Time for questions. So I will start. similar question, the sort of 2D, 3D nature of your results.
Okay.
So it's been shown that there's a very strong dependence on 3D for flapping, pitching, flat plates. And was the domain that you chose, are the sidewalls, are they periodic or implicit? What's that?
Oh, you mean the span-wide direction? And yeah, the span-wide direction is one code. But before that, I used 0.2 code, and they pretty much give similar results.
Okay. And is it just what's the boundary condition of the side?
Oh, sorry. It's symmetry.
Okay.
Okay.
So,
Yes.
one more question. Okay. So why did the CD, so as I understand it, as a function of frequency, when the frequency went high, eventually Cerefoil was producing propulsive force. Why? How do you explain that?
So it's kind of similar like how birds fly or how fish swims. So they change. Oh, sorry.
Right at the start.
Okay.
So why did you stop the simulations at that frequency? Why did you?
Yeah, because the thing is, at the beginning, I thought because we have like frequency in the tidal. We have wave there. So at the beginning, I think maybe I can generate more energy from that. But unfortunately, is that usually the frequency is very low, the natural frequency. So it's kind of impossible. So then we focus on fatigue loading reduction, not like generate more energy. Thank you.
Thank you very much. Good afternoon, everyone. My name is Nandini from University of Southampton. I'm presenting a 3D influence on the propulsive flapping at the Reynolds number. So me with my two supervisors, Gabriel Waimot and Bharat Ganapati Subramani. So as we can see from the bioflyers and the swimming animals, we can see that with the high aspect ratio fins or wings, they actually flap very efficiently. So according to the strip theory, if we have these long flapping wings or foils, we can integrate the coefficients of thrust or any force coefficients in each strip. Actually, we can get the total coefficients of thrust. So we can see here by the experiment result from Fu, each strip of the wing actually they undergo different flow structures, and it's actually a different Strouhal number. So my motivation for the research is actually a majority of flapping foil, they prefer to do it in 2D simulations. And actually based on several experiments and results, for example, here is our colleague, Luc Muscut. So he found out that his 2D simulation, the coefficients of thrust, the mean coefficients of thrust actually, of the experiments coincide exactly at the 2D simulations. So this experiment using a 10-degree effective angle of attack. But when we have simulations, here I'm comparing a steady foil. So the Professor Luc is doing a flapping foil at 10 degrees effective angle of attack, and while I'm doing a steady simulations at 10-degree angle of attack, it gives actually a very different flow structures, and there's a 10% of discrepancy between the coefficients of thrust and lift. So actually, a big question here, will the kinematic help to reduce the difference between 2D and 3D simulations? So my methodology here, I will present you the heaving, which is the moving ups and down, and pitching is the rotation. And the rotation point in here for pitching is a quarter of the chord length from the leading edge. And I will also present the couple motion, which is actually the combination with heaving and pitching with the phase of 90 degree. So according to some literature, you can see that the wake of flapping foil can be represented based on the amplitude-based Strouhal number, or I call it here Strouhal A. It's actually, it contains actually the amplitude and the frequency. So if we separate these two, amplitude and frequency, here I call it AD, and the frequency base of a Strouhal number based on thickness, I actually call it SCD here. So my research will actually, we fix the frequency and we will increase the amplitude. I'm using a Reynolds number of 5,000 and a thickness of NACA 0016. So no tip effects because I'm using a periodic boundary conditions. I will see the coefficients of thrust and coefficients of lift. And I'm using the CFD based on boundary data immersion method used by Gabriel Weimark. So he introduced this one first using a Cartesian grid and implicit LES, and also it is good for. It's also proven for good for a foil moving, with the Reynolds number up to 10 to the power of 5. And my grid density along the chord is 128 of the streamwise, and my span-wise is 3 times of a streamwise grid. So here I'm going to show you the result of the heaving. For example, here is on the, I'm increasing amplitude from the lowest ones, and I'm fixing the frequency. So, and I'm presenting here the mean coefficients of thrust. So at the lowest amplitude, or the lowest through hole, we see that the structure is almost like steady. It's a 3D flow structure, chaotic motion. But when I start close to the AD equal to 1, we found out that there's a 2D structures here, is a uniform 1. And when we increase more, we get the, it start to become chaotic again. Sorry. What I present here, when we can see that if there's a 2D flow structure, the graphic of the coefficients of thrust average between 2D and 3D actually it collides together. It becomes 1 point. But when the 3D structure appears, we can see that the separation between 2D and 3D. So for heaving, we have a very small window, but when pitching motion, the same we found here. Actually, we begin to have a very big window of 2D structures. And at coupled motion, we have the same big windows, but we have earlier 2D flow structures. So now we are seeing at the fluctuation of the forces. Previously, we just look at the mean CT. Now we are trying to look at the maximum average. So when we have the blue one in the middle, it's actually the area where the 2D uniforms. So when there's a 2D uniform, actually the trace of the CT is between 2D and 3D are the same. But when we have a very high amplitude or very high Strouhal number, the maximum actually fluctuates a lot at 2D simulations. At the lowest one also, if you have a very low Strouhal number, it fluctuates a lot at 2D simulations. So now we're looking at the phase average for TCT. What I'm doing here actually, on the two top pictures here, it's actually a 2D simulations. It's the instantaneous one, and then I average based on the same position, the whole simulation. We call it the phase average. At the bottom, at 3D simulation, actually I span-wise the average, and then I do the same thing phase average. So I compare between 2D and 3D, and we look at the lowest amplitude at heaving motion here. We can see that the difference between 2D and 3D actually is at the separation region of the foil. At the highest amplitude or highest Strouhal number, the emotions become very chaotic. So between 2D and 3D, the 3D is much more stabilized. So the difference is actually at the wake mainly and the leading edge. So, sorry. Now we are looking at the energy of distribution. I'm looking at the power spectrum now. If I integrate the power spectrum of the whole area below the curves is actually represent the variance or the energy of coefficients of thrust. And I normalize the axis based on the flapping frequency. So if you see the peak in the middle, it's actually the flapping foil. Now if I have the area of the white one, it's actually the area where the flapping frequency is. And the orange one is actually the frequency, the low frequency. And the blue one is actually the harmonics. Now, if we look at the heaving, pitching, and coupled, here I present you the coupled the pair of the bar actually is 2D and 3D. On the left is 2D and the other one is 3D. So the 2D is actually normalized to 3D. So 3D is always 100%, and we can see that 2D is actually at the lowest amplitude, and the highest amplitude, actually giving a big difference compared to the 3D. So what we can conclude here, actually, 2D is exaggerating the energy at the lowest and lower and the higher Strouhal number. So what I conclude here that we found there's a 3D flow structures at the lower and the higher Strouhal number, which is actually produced by a span-wise effect. There's no tip effect at all. And the 3D structure is actually accompanied by the different discrepancy between mean and maximum force coefficient, and the energy also different. And if you are using a strip theory, it's still valid, but only in a very small range of Strouhal number. And outside of this range, it's just better to do with 3D. In future work, we will do it in additional rolling motion, and we can 3D kinematics, we call it. Thank you very much.
Just miss. So in the regime when you have lift up, the lift to drag ratio is optimal or not?
Sorry, which one is it?
No, not the lock-in. When you have the lock-in of the frequency. When you have the 2D regime, yeah?
Oh, yeah?
So what happens to lift to drag ratio?
I'm sorry, I did not pay attention to lift, so we just focus on drag because this is propulsive flapping. But the tendency between lift and drag, yeah, thrust is the same.
Excuse me, you said you had one specific frequency, the flapping frequency, right? But in nature, usually when something flaps, it starts from 0 to, let's say, 0.4. Did you take into account this gradual change into your simulations, or did you just start from the chosen frequency?
Well, actually, when we are increasing frequency, we're actually basically increasing a frequency, and all the normalized frequency is based on each flapping frequency. Is that answering the question? Thank you.
Hello. Hello, everyone. I'm Omar from Imperial College London. I'm working with Andy Nguyen and Sylvain Lizet. What we're trying to do is using Bayesian optimization in order to reduce the skin friction drag and the net energy of turbulent boundary layer by optimizing the parameters of wall blowing. It's well known that around 50% of the energy spent by an aircraft is due to the skin friction, and most of that comes from the wing and the fuselage. And if we successfully reduce the net energy of the aircraft by 3%, we can save millions of dollars and tons of carbon dioxide emission per year for just one aircraft. There are many techniques have been developed over the past years to reduce the skin friction drag of turbine flows, but most of them are not practical for real-life applications due to low efficiency or due to complexity of the control algorithm. So here we are focusing on wall blowing or wall respiration. If we have a permeable wall with pressure difference on both sides, we can have a uniform blowing or uniform mass flow rate from the surface, and that can reduce the skin friction drag, the skin friction by around 50 or 80% for subsonic and supersonic flows. And the important thing is the flow rate of the blowing is very significantly small, and the effect of the drag reduction can extend further downstream. But still, the energy expenditure by the blowing system is very high and can exceed the energy we save by reducing the drag. So the research objectives are to build a Bayesian optimization framework in conjunction with DNS and LS to achieve drag reduction and net energy saving, and to test this framework to see how fast it can to reach the optimum parameters for wall blowing. And also, we'd like to understand the mechanism associated with drag reduction with wall blowing. For the numerical simulation, we're using InCompact 3D. It solves incompressible Navier-Stokes equation using sixth order compact finite difference in Cartesian mesh. For time advancement, we use semi-implicit. Also, Poisson equation is solved using spectral solver. And this code is very efficient running on large machines up to 100,000 cores thanks to MBI and 2D decomposition of the domain. We're doing DNS simulation on this domain. And we have a laminar profile at the inlet with tripping in the beginning of the domain. And at the outlet, we solve 1D convection equation, and the Reynolds number at the inlet can reach up to 1800 based on the streamwise velocity and the momentum thickness. This is the control region where we apply the blowing. And this control region could be uniform blowing, or can be divided into stripes of solid wall and permeable wall. And the parameters we're controlling or changing are the streamwise length of the solid area and the blowing area. Also, we control the velocity of the blowing. To make sure that we are solving finite scales, we compare with Schlatter 2010 and Stroh. We find a good agreement with in the skin friction coefficient and the mean velocity profile and the root mean square of velocity fluctuation. For Bayesian optimization, Bayesian optimization works in two stages. First one, it creates a probability density function using a Gaussian process to estimate the objective function with some sort of uncertainty. Then we use acquisition function to trade off between the uncertainty of the objective function we calculate and the value of the objective function. In this study, we're using expected improvement. We found in the literature this is the best thing to use. To simply explain how Bayesian optimization works, let's start with 1D example here. So if we have the black line here, this is the true objective function. Typically, we don't know it. But if we can start with any arbitrary value, so to determine the objective function, we get it here. So we have low uncertainty here, but the uncertainty here is very high. And we can somehow estimate the objective function. So the acquisition function will decide to go to low uncertainty to pick another point to calculate the objective function and keep going until it fit the true objective function with relatively low uncertainty, so we can know with low uncertainty that we are, this is the optimum point. In our study, we're optimizing three parameters: the streamwise distance of the blowing region and the solid region, and the blowing coefficient, CB. The blowing coefficient is the ratio between the wall normal velocity and the free stream velocity. Also, the objective function is the net energy saving, and it's a function of four parameters: the skin friction coefficient, the blowing parameter, and alpha. Alpha is the ratio the area ratio of the blowing region to the total area we calculate the drag on. And we have the third parameter, the pressure coefficient, is the pressure drop between the blowing surface. We don't have this, we can't calculate this, or it's hard to calculate it numerically, so we use the experimental data from Kornilov and Boyk, 2012. And the CP is the pressure coefficient equal to 1/24 of the pressure of the blowing coefficient. We need a turn iteration to confirm convergence to the minima. And we base on the global drag. The global drag is the average of the local drag over Reynolds number between 360 and 1700. This number is where we have a fully turbulent boundary layer. We find in case number 13, which is the iteration number 13 by Bayesian optimization, it has the highest net energy savings, around 5%, and this is achieved by uniform blowing at around 3% of the stream free stream velocity. And for case number 5, we achieved the highest drag reduction, around 76%, and the global drag of 19%, with a blowing coefficient around 1% of the free stream velocity. But we increased the net energy by 21%, and we have the friction coefficient function of Reynolds number, we can see here in the blowing region, the friction coefficient suddenly drops. And for the case number 5, the blue line, it fluctuates here due to the intermittency of the blowing. And far downstream, we have the drag still low, and it converges slowly to the canonical case. This is an instantaneous visualization of the flow using Q criteria. And we can see here, over the blowing region here, this pink area, the turbulence activities increases dramatically for both cases compared to the canonical case. So this arises a question is how we reduce the drag and at the same time we're increasing the turbulence intensity. The answer comes from FIK identity, where the skin friction coefficient is decomposed into 4 components: the boundary layer thickness contribution, the Reynolds stress contribution, the mean convection contribution, and the spatial development contribution. We average all these quantities in this, the streamwise direction into locations, the control region and downstream of the control region. And we find that the spatial development and the Reynolds stress contribution increases dramatically in the control region. But to counteract this effect, the spatial development, the mean convection contribution reduced significantly to achieve drag reduction. But downstream, we find completely the opposite effect, where the mean convection contribution increases, but the spatial development contribution reduced. So we find 2 mechanisms for drag reduction. In the control region, the drag reduction is achieved by reducing the mean convection contribution, and downstream, the drag reduction is achieved by the spatial development. To conclude, we use Bayesian optimization with DNS of turbulent boundary layer and the experimental data to optimize the wall parameters in order to obtain net energy saving. The net energy saving we achieved is around 5% using uniform blowing with 3% of the free stream velocity. And we find 2 different mechanisms for drag reduction in the control region and downstream. 5% of net energy saving is still low. And this is for 3 reasons. The first one is we applying the control, in our simulation, we only simulate at low Reynolds number up to 1800, and the control region length is very small. So in the future, we're going to use LAS to test high Reynolds number. Also, the blowing system could be inefficient. Therefore, we're getting a new experimental data from Richard Willey from Newcastle. His blowing system could be more efficient than the one that we used in this study. Also, we would like to investigate more parameters of wall blowing. And thanks for listening. Say it again, so I don't understand what you mean by changing.
I was wondering what your sampling time was for the DNS averaging.
Yes.
You need to change that for the warbler.
No, I didn't change it. No, I didn't change it. Because here we're focusing on the skin friction, and it's not very sensitive to the sampling time. Of course, if we care about the loss fluctuation, yeah, we should care about it.
Yeah, hello, good afternoon, everyone. I'm Fang Xu from University of Manchester. Now I will give a brief introduction of my work of span-wise heterogeneous roughness and its flow control effect. So let's begin. For the span-wise heterogeneous roughness, it indicates that its span-wise length scale is comparable to the boundary layer scale pipe radius or some other dominant parameters of the flow field. So we call it span-wise heterogeneous. The main character of it is that it can induce large-scale secondary flow within the cross-stream plane. So we are very interested in this. We have many engineering applications, and also we have different type of span-wise heterogeneous roughness, like the span-wise alternating rough and smooth surface, or our convergent divergent riblets I will introduce later. And also I want to address Pronto's secondary flow. It has two kinds. The first kind is called geometry-driven. So it's an invasive process. It is driven by the geometry of the flow, of the surface texture. And also we have the second kind. It is driven by shear or turbulence. So for this flow, it is driven by the imbalance of the stress within the flow field. And of course, it can only happen in turbulent flow field. Now, my configuration is a nature-inspired surface texture. We name it convergent divergent riblets, or just CD riblets. It is inspired in nature from both shark skin. It's not all the part of shark skin, but only a certain part of the sensory receptors of it, and also the bird's secondary flat feather. For this, we have different applications like drag reduction, separation control, and heat transfer augmentation. You may argue that for these two applications, we may consider it as a low-profile vortex generator. So this is the configuration of our surface texture. The flow is from top to bottom. And we have some key parameters. Like the Euro riblets, we have the riblet height, riblet spacing. And also here, we have yaw angle and riblet wavelength. The wavelength is a span-wise length scale of this heterogeneous roughness pattern. So this is our experimental facility, just the schematic of the stereo PIV. We apply dye-visualization, mono PIV and stereo PIV to explore the flow field. In my report, I will give the micro and large-scale vertical structures, try to understand the flow topology. Later on, I will show its impact on the vertical structures, the velocity field, and also investigate the riblet wavelength, because it's a really important parameter of our texture. So first is the dye visualization result. You can see it's composed of two figures, the side view and the top view. So it happened at the same time. And we can learn many things from this figure. First, I explained that dye is injected from 5 holes from upstream, and then it flows close to the surface. So mostly it reveals the vertical structure close to the surface. We can see the positive vertical velocity near the converging line, just away from the wall, because the wall is the upper side. And also we can see span-wise flow from diverging line to converging line, because it flows like in this way. We can see some overflows above riblets. These overflows are really important, because they will help explain the velocity fluctuation we can introduce within the flow field. We can see some overflows, and it is flowed from the diverging line to the converging line. So we introduce small fluctuation to the converging region. And also we can see the helicoidal path I will address in next slide. And also we can divide the flow field in two stages, the developing stage and followed by the developed stage. And we also have some other parameters to validate this. So first, the helicoidal motion. Because we have dye visualization, because for experiment like PIV, it's really hard to get the flow field within the grooves. But for our current case, we can get the helicoidal motion. And just like here, it's not involving along the channel directly, but just swirls inside it. It is composed of the axial component and the cross-channel component. All they together contributes to the helical involvement. We can also show the effects that for downstream stations, it will have longer pitch. That is a longer time to involve a circle. So it means a higher axial velocity within this region. So for the cross-stream plane, we have very intense we can say it intense secondary flow within this plane. And also, it's a co-rotating vertical structure just within half wavelength. We have the primary vortex and the secondary vortex. For the formation, we don't have time to address it. Yeah. So this is the flow topology following the above observations. We have downwash close to the diverging line, the upwash close to the converging line, and also the formation of the co-rotating vortex pattern. So we have now we have understand the flow topology. Our question is, how will it affect the flow field? For this is the vorticity. You can see the uplift of the high shear region. But for the sand swirling strings, so it can only reveal the only rotational part. We can see the periodic distribution and very intense rotation along the diverging region. This is done in the wall parallel plane. So in wall parallel plane, we can also see the difference between developing and developed stage. For the developed stage, we can see some of these spots. It can be known as the footprint of the vertical structure within this plane. So this is just a velocity. This is rather apparent, as we have revealed in the dye visualization. We have near converging line. We have the positive wave velocity, and also the local velocity of streamwise just decrease. The opposite happens to the diverging line. Now we take a little bit at our riblet wavelength effect. For wavelengths, the interesting thing I want to address is that even for larger riblet wavelengths, it leads to reduced width of affected region near the diverging line. So it is opposite to what we have thought about, but it is a fact. So also we try to integrate between within a wavelength, try to reveal how will it affect the whole flow field. As we have shown in this figure, this surface texture leads to global deceleration effect if we integrate within a wavelength. So I just gave the conclusion. Our experiment is the first experiment that proves this surface texture can induce Parental's first kind of secondary flow. Because I have argued that for Parental's first secondary flow, it can occur in both laminar and turbulent boundary layer. Our case is laminar. But for Parental's second kind of secondary flow, we just call it second kind. It can only occur in turbulent boundary layer or turbulent flow field. In our laminar case, we can still observe the rotation, the secondary flow within the cross-stream plane, so we can validate its Parental's first kind. Also, we can show the boundary layer in 2 stages. I haven't addressed much detail in previous slides. It's just some parameters level off within the developed stage. So there's a difference between these stages. And also the flow topology. The thing we want to address is helicoidal involvement inside the riblet valley. It's not involved along it directly. And also it's profound impact on the flow field and also the rotational motion and also the global deceleration effect. We also reveal the riblet wavelength on the vertical structures. So we have published our results. If you want to know a little bit more details, please refer to it. Okay, thank you. Any questions?
Just a couple of minutes, any questions?
What's their primary motivation from the research?
Frankly speaking, for the current laminar research, my ultimate goal is to reveal the flow topology induced by this surface texture. Because in turbulent one, we have coherent structures, and we can have more engineering applications. But we can't have very stable structures within the turbulent boundary layer. But in our laminar one, we can observe some stable vertical structures within a certain part, and we can apply some other methods like dye, have very stable dye involvement, and know the flow topology. So for turbulent one, our first ultimate goal is drag reduction. But for this surface texture, it introduces disturbance to the flow field. So it may not lead to a drag reduction, global drag reduction, I should say. But it can lead to local drag reduction. And also, for this, as we can see, it induces large-scale secondary flow, introduce some new vortices. We can expect its control on flow separation and heat augmentation. Okay.
Very quickly, so you said you believe all the flow fields that you've seen are steady. You've only shown us average.
No, it's not really very steady, because for the overflow part, it's not steady. Yeah. Yeah. Thank you.
Okay, I'm going to be looking at the stability of low-speed streaks that are formed when you have a short span-wise scale injection into a flat plate boundary layer. So here's a schematic for the problem. So this is the injection region, and so there's an oncoming uniform flow or possibly a power law flow, and the pressure gradient is parameterized by this beta. The zeta naught is the width of the injection slot, and we're taking the Reynolds number to be large. So the thing to note is that the injection grows at the same rate as the boundary layer thickness, so it's self-similar downstream. Okay, so in a usual 3D boundary layer formulation, you just have the one boundary layer scaling. So that's usually the transverse coordinate, the y there. But in our formulation, you have to include the diffusion, so you have to have the z coordinate as well. So if you remove the z dependence, then you get the usual Faulkner-Scan or Blasius boundary layer. So when you include the z, you get these extra diffusive terms. So these are called the boundary region equations, or the parabolized Navier-Stokes equations. So yeah, so the thing to note is that the extra diffusive terms makes it slightly different to the usual 2D problem. So first I'm going to have a look at the self-similar solution, and you have these similarity variables. So that's the transverse and the span-wise coordinates. And we're going to have an injection over a finite region where it's a top hat profile, so just having injection and no injection in the 0 to 1 area, and then the rate of the injection is parameterized by K. So first have a look at the case where there's no pressure gradient. So when you've got a weak injection, then you don't really get much variation from the usual 2D boundary layer, so you get a slight thickening near the center of the injection region, but there's nothing much happening. If you increase the injection, then you start getting this formation of a low-speed streak. So when you have a moderate injection, the streak is contained within the injection region, and you have a low-speed region separated from a high-speed region by a shear layer. Then if you increase the injection even further, then you get this semicircular streak being formed. So when you have zero pressure gradient, you have these three delineated regimes. So when you introduce pressure gradient now, what you find is that the delineation between these regimes sort of breaks down. So like the weak injection regime, there's not really much difference. But for the moderate injection and the strong injection regime, you see that the extent of the low-speed streak is really reduced. But you still have a streak formed, but it's just much more contained within the injection region. Okay. So if you have a small pressure gradient parameter, and then you increase the injection rate, so you have a large injection rate, you get this eruptive behavior close to the center line. So the streak is a definite low-speed streak, and then it sort of moves upwards in towards the high-speed region flow. But when you have a sufficiently large pressure gradient, then what you get is the usual Faulkner-Scan solution out here, and then you get a Faulkner-Scan solution, but with a 2D injection, and everything is nice and controlled near the center line, so you don't get this eruptive behavior anymore. So you can see this when you look at the profiles of the velocity on the center line. So when you've got a high pressure gradient above some critical value, then so here this is the Faulkner-Scan solution that you would expect, the parabolic solution. And here is with an increasing. So this is like the asymptotic solution, and there we have a solution with a numerical solution with 20 as the injection width, and then there's 40. So when it's a large pressure gradient, then these all fit on the same. They're all the same basically, and then but when you have a smaller pressure gradient, then you get this deviation in between the. So they agree close to the plate and far away, but in the middle there's this deviation. So here we have a look at. So this suggests you get a spatially unstable eigenmode as you go towards the center of the injection region. So the thing to note. So this is an eigenvalue problem, and we have. So here's the injection rate's increasing this way, and then this is for different increasing pressure gradient parameters. So when the eigenvalue is negative, that means we have a spatially unstable eigenmode. So this is a plot of the critical pressure gradient at which you get spatially unstable modes being introduced. And so as you can see, when the injection rate becomes large, this sort of settles down to a value of a half. So the thing to note with these injection things is when you have a zero pressure gradient, you get 3 distinct regimes, but then when you introduce the pressure gradient, then the delineation between the 3 regimes breaks down. And then if you have a pressure gradient above some critical value for a large injection, you get a stable eigenmode, and you recover the Faulkner-Scan solution with injection at the center line. And but when it's below that value, then you get a large deviation from what you'd expect because of spatially unstable eigenmodes. So the streak flow that we have now, I'm going to have a quick look at the stability when we introduce a traveling wave disturbance. So we have a traveling wave with a wave number alpha, the frequency omega, and the wave speed c. So here we've got the solution we had before, so these give you the streak equations. And we have this a wave, so we've got the wave velocities in the 3 directions and the wave pressure. And this has this Reynolds number to the half scaling in the wave, traveling wave. So when you go through the equations, you get this system here where these are the even and odd functions. And this is a 2-dimensional version of the Sommerfeld equation. So you have this Reynolds number here. But obviously the streak solution really works when you have a very large Reynolds number, and it's in a large Reynolds limit. But you can approximate it if you have a sufficiently large finite value of the Reynolds number. So this is because it's to the half scale in there, so the Reynolds number to half is 1,000. So if you look at the streak, this is the in-plane wave velocity. So you get a concentration in a layer, and so this is so when you increase the Reynolds number again, you get this. It continuously concentrates in this thin layer, which is so this is the wave, the eigenfunction. So if you can have a look at the most unstable eigenvalue, so you can see that. So when this is above 0, then the wave's unstable. So these ones are slightly unstable eigenfunctions. But you can see that as you increase the injection rate, then you get the more unstable mode, and when you increase the wave number, then it becomes more stable. So really, this only works if the Reynolds number is really large. But you can take the inviscid limit of this. So if you take the inviscid limit of the linear, and you get the inviscid linear stability equations, you get a 2D version of the Rayleigh equation. But this is in terms of the pressure rather than the velocities, but we can transform between them using these equations. So you can see that in the large Reynolds number limit, then you get this critical layer formed. And so this, what you can do, the problem with solving this Rayleigh equation is when you've got a C that is in the neutral mode, then this becomes singular, so you can't solve it. So when we plot the eigenvalues, you can see that you can't actually get down to 0 because it becomes numerically unstable. So the Sommerfeld equation that we had there is much more useful when you actually want to solve these things numerically, because you can actually get down to the neutral mode. So the 2D or Sommerfeld equation provides a good approximation for the Rayleigh equation, and because the streak equations are only valid when you have a large Reynolds number. So the inviscid 2D Rayleigh equation is the only one that's asymptotically consistent, but obviously when it becomes singular, it becomes problematic to solve numerically. So you get this, when you have a large Reynolds number, you get this concentration of the eigenfunction in the critical layer, and you have sort of the concentration, the unstable modes are sort of concentrated there, and that will so what we want to look at in the future is the interaction between the waves and the streak, and see if they can produce a sort of self-sustaining structure. So so this is what we're currently working on. So you have interaction between the streak and the wave, and so you get the hope is that if you reduce the injection rate down to 0, but then increase the amplitude of the wave, that you can still maintain the streak structure. But obviously, it'll be slightly different than what you'd expect when you have an injection. Thanks. I'll answer any questions.
Any questions? A quick one. Yeah.
So is the hope that the end to find an exact coherent structure?
Yeah, but it's not really working at the moment. Yeah.
Hello, I'm going to be presenting my work on predicting shark-skin boundary layers using the RANS models. So I'm going to introduce the shark-skin problem by having a look at shark-skin. I'm going to be talking about how the shark-skin problem is quite unique to these RANS equations. And then I'm going to be looking at the research question of this presentation, which is investigating numerical errors associated with these small cell sizes that are associated with this shark-skin. So to introduce the shark-skin, this image on the left of 3 samples taken on the same shark, and you can see there's a lot of variability between these different scales. They're made of bone. They've got a typical width of 100 microns, so they're very small. And they vary a lot between different species and different sharks. And they're interesting to engineers because they passively reduce drag. And this is different to most fish that excrete mucus for active drag reduction. So what's been done already? Most focus has been on riblets. We've seen a few talks already today on riblet flows. And in terms of streamwise parallel riblets, these can typically reduce drag by about 10%. And there's very good agreement between the literature data on these flows. But there's lots of features in these shark scales that haven't yet been investigated. For example, there could be flow underneath these kind of structures that could be interfering with the boundary layer. And these things haven't been really investigated. And the experiments that have been done on these flows are very... They don't agree at all, really. So some of them say that the real shark skin actually increases drag more than riblets. Some of them say it decreases by quite a lot. So what I'm interested in is understanding what other geometries could possibly be used to reduce drag. And alongside experiments in DNS, I'm going to be using RANS methods to do this. So why is this a unique problem for shark skin? What's unique about shark skin is that these structures are so small that the near wall cell size in order to resolve these geometries is actually much smaller than y plus values of 1, which are typically used for these RANS problems. So if you were to, say, investigate a range of S plus values, where S is the spacing between the riblets on the top of these tentacles, if you were to investigate a range of these sizes, you'll see that your y plus values range by at least an order of magnitude, maybe 2, over your full simulations. And if there's any dependency on your solution on y plus, then you'll find that this could really pollute your drag data. So I'm expecting that since my friction velocity is going to vary by maybe 10% over these different surfaces, y plus will vary by several orders of by at least an order of magnitude. And just to illustrate how Y plus varies over these kind of surfaces. I've got here a periodic flow over a shark skin surface, and you can see that Y plus, for a moderate S plus value of 16, is already down to 0.16, and I would quite like to get down to S plus values of 5, up to S plus values of 50. So this leads me on to the topic of this presentation, which is estimating the numerical errors associated with solving Rand's equations with these small near-wall cell sizes. And to do this, instead of looking at shark skin, I'm actually looking at a 1D fully developed channel flow at a moderate Reynolds number. And I'm going to be varying the near-wall cell size delta 1 from about 5 times 10 to the minus 4 to a Y plus value of 2.5. And in that range, you'll see that some of these models behave very well, and others give solutions that are very dependent on this cell size. So here are the Rand's equations. I'm not going to go through them, but the way so we've got the Rand's momentum continuity equation at the top, turbulent viscosity hypothesis to close the Reynolds stresses. And the way you model nu-t is using 2 equation models here. And these solve for transport equation for K. And in our first case, which is the K omega model, we solve an equation for omega, which I've chosen because it's typically used in industry for giving reasonable predictions of boundary layers. And this is because without having to use any damping functions that significantly change the behavior of these models, they can get reasonable predictions of boundary layers. But there is a problem with this model in that near the walls, omega goes like 1 over y squared. And there's been a little bit of work in order to estimate how large this error can be when you're trying to discretize a function that goes to infinity at the wall. But what engineers typically do is either use a wall function to impose omega at the first cell near the boundary, or they use a kind of rough wall approximation, which essentially ignores this and equates omega to a kind of roughness constant on the wall. And what I'm going to do is compare these to some turbulence models that were released in 1996 and haven't seen really any development or use since they were first published. And what Kalitzin has done is formulated a new model by substituting in omega equals 1 over tau into the K omega equations and solved for tau instead of omega. And what's good about this model is at the wall, at y equals 0, tau equals 0. In addition to this, he's also looked at a KG model where omega is related to g by 1 over g squared. And the benefit of this particular model is that it's linear near the wall rather than quadratic. So these models are mathematically equivalent to K omega, so they should give predictions that are identical. So any differences that I see will be entirely associated with the discretization of these models. And so here's the first result, where I'm looking at friction velocity prediction, where C5 is the finest case compared to varying near-wall cell size. You can see that the general rule of thumb, which is to specify a y plus value of 1 near the wall, gives us a 2.5% error for the standard K omega model. And if I just relate this back to the shark skin problem, we're expecting to see drag reduction of the order 10%, 5% maybe. And that would heavily pollute this data towards the higher values of S plus that I'm looking at. And so this is really not feasible to use. And I'd have to get my Y plus values all the way down to 10 to the minus 2 in order to eliminate this error entirely. You can actually see that this error is made worse when you include rough wall boundary conditions, which is what this K omega 2 solution is. In contrast, the K tau and KG models show almost no dependence on Y plus, as long as you're below kind of Y plus of 1. My first, at this point, that's a Y plus of 0.5 here. And the error up here is associated with more of a modeling error where the mesh isn't fine enough to actually capture the viscous sublayer fully. So that's a Y plus of 2.5. And so you can see that just by changing these equations, you can eliminate this mesh dependency error. And this has large implications for my work, despite these model's not really being used at all in the last 2 decades. But I imagine it also has a lot of implications in, if you're looking at drag reductions over, say, aerofoils, where skin friction can be of the order of 50%, and these 2.5% errors could play a difference there. In order to investigate kind of exactly why this is happening, if you plot omega against, normalized against omega nu, where omega nu is the asymptotic solution that you can get from perturbation methods, you can see that the k-tau and kg model predict this almost perfectly. You can see there's a small discrepancy for the k-tau model here, but this is negligible over the rest of the domain. In contrast, the k-omega models overpredict omega by over 50% in the first cell away from the wall. Sorry, the second cell away from the wall. The first cell next to the wall is fixed at omega nu by the imposed boundary condition. And you can see that this has a big impact on a lot of the cells as you get further away from the wall. And it's only, I hypothesize that as long as your cells are small enough that this kind of overprediction is limited to below your kind of viscous sublayer, that you don't get any issues carrying on into the free stream. So I haven't got long left, so I'm just going to nip to the conclusions, which are that if we are to kind of look at these, look at problems where the cell size is small, it's really important that we make sure we have a model that can give us friction velocity predictions that are not a function of how small the grid size is. And I found that the k-omega model, which would be typically used for these kinds of flows, results in very large errors near of the friction velocity, which can be removed if you solve for either g or tau instead. And in terms of further work, I'll be extending these to Reynolds stress closures and then returning to the shark skin problems, hopefully get some predictions of those geometries. So thanks for listening.
Maybe one question.
So why are the k-tau and kg models used much less than the omega?
Yeah, that is an interesting question. I think for most CFD applications, you're trying to get down to these cell sizes where you actually notice this kind of error is very rare. And in most cases, even getting down to y plus values of 1 is essentially infeasible. And above that, I don't think you would notice any benefit of using the k-tau and kg. I think that's essentially why. So.
Thanks. So my talk's about an experimental investigation of shock boundary layer unsteadiness. So I'm just going to jump straight in and explain what shock boundary layer interaction, or SBLI, is. So as the name suggests, wherever a shock wave impinges on a boundary layer, you get an SBLI. This is a cutout of a supersonic engine intake, and it shows a compression ramp interaction here and a instant reflected shock interaction here, which is what my experiments are. So an instant reflected shock boundary layer interaction occurs when the large adverse pressure gradient across the instant shock separates the boundary layer. The oncoming supersonic flow sees this separation, and compression waves form ahead of it and coalesces the reflected shock. And it's the interaction of this reflected shock with the boundary layer which is what we're interested in. So a long time ago, Ehringer and Dolling characterized the compression ramp interaction. Again, they're interested in the interaction of this reflected shock with the boundary layer. So what they did is they took pressure measurements under the interaction, and they recorded the pressure fluctuations, and they found the power spectral distributions, which look like this. So starting at station 1, so this is up here in the upstream boundary layer, the frequencies basically scale with the free stream velocity divided by the boundary layer height. So as you might expect, high frequency boundary layer fluctuations. Then as you start to measure under the reflected shock, it shifts to frequencies 1 or 2 decades lower. And then as you carry on, it sort of recovers back to the high frequencies. So obviously this is interesting. Firstly, there's no obvious source of these low frequencies. And also these are important from a practical point of view. So if your shock is oscillating at a low frequency, this is associated with a large amplitude motion. And again, across the shock, you have that big jump in pressure. So that's going to fatigue your engine intake, for example. So what researchers do to try and characterize this frequency is they non-dimensionalize it into a straw hole number. So they times it by the separation length divided by the free stream velocity. And what you find is that for a whole range of different interactions, the straw hole number is around 0.03, although there is some spread. So one possible reason for this spread is because we tend not to account for the three dimensionality of interactions when we're studying them. So that 2D engine intake that I showed earlier is in fact part of usually a large square intake. So for example, this is the Concorde engine intake. Experiments are typically conducted in a square duct with a wedge. This is our wind tunnel, for example. So that 2D separation bubble that I showed earlier, perhaps we need to start thinking that for what it is, which is very much a three-dimensional, varied separation region. So this is the LES of Wang et al., and they showed that you can see, even on average, it's non-uniform across the span. You also get corner separation as the incident shock interacts with the sidewall boundary layer. We characterize the three-dimensionality of our wind tunnel. So this is oil flow visualization. So we're basically injecting paint into the floor of the wind tunnel, and it settles in regions of low skin friction, so separation reattachment point. So from this, we can pick out our separation region. Two things to notice. So we have a large corner separation, which you can see here. And also, even in the experimental environment, the separation is highly three-dimensional, particularly on this near-side plane. Previous work in the group showed that for an interaction of one strength, changing the height of the shock generator and the thickness of the shock generator gave a whole range of separation lengths. So again, perhaps just considering the sense line isn't going to collapse our straw hole number, this graph that I showed earlier. I wanted to just highlight, so these were all experiments conducted in Marseille in France in the same wind tunnel for an instant reflected SBI. So you might expect that as you increase the, going up there, decreasing the strength of the interaction, you might expect that the straw hole number would collapse. However, for this configuration, decreasing the strength was increasing the aspect ratio, which Grossman showed tends to increase the separation length. So this, for example, could somewhat explain the spread and straw hole number that we see. So just, Nonetheless, the majority of experimental studies will just take measurements along the sense line. The majority of numerical studies employ span-wise periodic boundary conditions, and both will just assume that there's span-wise similarity, which Grossman showed is not the case. One recent numerical study which did employ sidewall boundaries was done by Jamy and Sandham. So there's a sidewall at 0 and 100 mil, equidistant from this central plane here. And what they actually found was the most energetic straw hole 0.03 was off-center. So they attributed this to their short run times. They said the study wasn't converged. They captured 23 low-frequency periods of this unsteadiness. That's actually quite a lot for a numerical study, because you have to capture the high-frequency boundary layer fluctuations of order U over delta. But then you need to run your simulation for 100 U over delta, for example, to capture one of these low-frequency periods. Experimentally, we have the advantage in one experiment, we can capture about 6,000 cycles of the low-frequency behavior. So with that in mind, we wanted to produce the first experimental low-frequency unsteadiness map and compare to the results of Jamy and Sandham and ascertain if this asymmetry is in fact an artifact of the lack of convergence. So you can see here our the sort of strength of the interactions is about the same. Theirs has twice the aspect ratio, so it might be considered more two-dimensional. The experiments were conducted in the Imperial College Supersonic Wind Tunnel. We build up pressure in the settling chamber. It is accelerated to Mach 2 through the converging diverging nozzle and into the working section, which is 15 centimeters square. So again, converging diverging nozzle, Mach 2 flow sees the shock generator, which is a 12-degree wedge. Instant shock is generated, which separates the boundary layer, and you get a reflected shock ahead. We take pressure measurements under the reflected shock, and we get a history that looks something like this. So that low-frequency motion is like an upstream meandering of the shock. There's 10 pressure sensors in the plug. The plug can be placed in 8 positions in the floor, and the shock generator can also be moved up and down 2 mils. So we have a total of 400 measurement locations all to map out the low frequency unsteadiness under this reflected shock foot here. And this is what it looks like. So similarly to Jamyang-Sandam, it has this asymmetry, despite the 6,000 samples arguably quite converged. If you compare it to the oil flow, it seems perhaps that the high energy, low frequency content is related to the tortuousness of the separation line, which reflects the reflected shock itself. And then going back to that graph that I showed initially, again, the asymmetry is immediately obvious. And again, comparing it to our oil flow, so this is just one streamwise location now where the most energy was observed at the center line. So you can see that as this line meanders, we capture more and less low frequency power. So this is the big peak here corresponding to this point. And then we also capture a bit of the some quite high energy in the low frequency content in the corner separations. So I just wanted to focus on those measurements quickly because this is interesting. So from a measurement taken here, you can see there's low frequency power. So this sort of begs the question, can this be contributing to the unsteady behavior that we've been observing at the center line for all these years? So similarly to Jamyang-Sandam, I took the cross-correlation, which is basically the convolution of the pressure signal at the wall with the signals more inwards. So this is what they look like. So my data, there's no data here because the plugs just span a quarter span of the tunnel. However, it seems to be in fairly good agreement. This length of significant correlations is pretty much the same as the width of the corner separations. That implies that perhaps the fluctuations in the corner separation are completely self-contained and separate from those in the core separation. Oops. And then for completeness, we also looked at the correlations from the center line moving outwards. And similarly to Jamyang-Sandam, they sort of lose significance beyond about 35 mil. Although they're perhaps more, stretch more a bit on the more tortuous side of the separation region. So basically, in summary, I think that this shows that just looking at the unsteadiness at the center line, we can't expect to see a collapse in through a whole number. It's not perhaps truly characteristic of the interaction. And what I'd like to do in the future is to look at more interactions of the same strength, for example, those of Grossman, and see if we can relate the separation region characteristics to the unsteadiness characteristics, and then use that to, mitigate this low frequency unsteadiness some way.
Any questions for Paige?
Does the injection hole of the oil not affect the unsteadiness?
It's a good question. So I actually do, for each thing, I do 2 runs. So there's like a hole in the center and there's some off-center holes. So I do one run injecting through the center and a separate run where I inject like a quarter span, and I see the same patterns.
Right.
Yeah.
And the hole itself might have some effect.
It doesn't have zero effect for sure, but I don't think it massively affects where the thing is separating.
Same question.
Yeah, I can show. I've got another oil flow. So, well, you basically see this this necking thing on a different configuration as well. I don't have a picture, but then I did another run with a hole down here, and you still see the same sort of wavy pattern. I'm fairly convinced it doesn't have a large effect. Thanks.